Good evening, guys. Okay.
Hello, teacher.
Hey, how are you, Breno? Okay, so we have 25 people in already.
Yeah. Oh, teacher, I sent you an email probably 5 days ago. I don't know if you have checked it.
I didn't respond. I want to say the answer is no. Okay. So let's see. So we don't have, so we cannot find a decent set of,
Hours for those days.
yeah.
And that's the first thing. And the second is that classes are still missing in Paideia.
The second would be what, sorry?
The recorded classes are still missing in Paideia.
Oh, the lecture recordings, they're not
Yeah.
posted on IDEA system yet. Okay. Okay, awesome. Not to avoid delaying the lecture time today, I will do that after the lecture is over. I don't know what to tell you guys about the office hours though. That is rather unfortunate.
Yeah. What I thought is that it could be more than beneficial to maybe take 5 minutes at the end of the class, or maybe right now, for them to fill the schedule I send them. But
right now,
today,
the problem is that just as it is, right, it implies that, you know, in the best case scenario, we're going to find a spot where at least 7 people cannot make it, right?
yes,
Which is not ideal, but you know,
yes,
that's a problem. That's a problem. Let me see. The other thing we can do is, like, in principle, you guys shouldn't, well, but that's, I mean, we can always have it on a Thursday, right? The problem is that we have lectures on Thursday, so that's kind of the same thing. And you guys said that on Saturdays you also have lectures and stuff, right?
yeah.
Yeah, I refuse to do this on a Sunday. You probably would, probably wouldn't either.
I mean, I would, but I don't know.
Right.
Not everybody will be okay with that.
Okay. So let's try to wrap this up then. I mean, I'm at a loss, you know. I mean, the best thing that could be done probably is if we can have an idea whether people are going to be available in the time slots that we provided. Alternatively, you know, you could try proposing a time slot too. Like I don't know if there would be, you know, a time slot that would be convenient for everybody or for mostly everybody. But alternatively, we can do that and try to see if that can be fit into my schedule. But you know, yeah,
Yes.
I'm at a loss here. Yeah, I don't know what to tell you.
Oh, okay. I guess
I don't know, either I
manage
lazy
that.
it out, like you have no idea when I was a student, or I don't know why you guys have such a busy schedule, you know, it's like, that's amazing. To me, it's like uncanny, but sure, okay.
Yeah. Oh, yes. Also, last semester we had this kind of remember class for Fourier properties. I was wondering if this semester we're going to have the same class.
Sorry, what? Which class, sorry?
Last semester we had a class to remember Fourier transform properties.
Right.
Yeah,
Didn't we
but this semester
have
we
that?
still, no.
Didn't we have that already?
No, we didn't.
We didn't, really?
Yeah. It was supposed to be on Thursday, the last week, but I thought you modified the PPTs to because of the time.
So on Thursday last week, I'm at the Paideia side right now. Like you said, Fourier transforms, because I mean that we did on week 1.
No, we didn't go to.
Looking at the no, I mean last week on Thursday we did ultrasound, right?
Yeah.
Right. Okay, let me see. Like maybe I'm missing something in here. Okay, let's talk about this. Like in order to avoid delaying this, let's talk about this maybe after the lecture is done.
Yeah.
Okay.
Yeah. Fine.
Okay. Okay. So let's get started with today's lecture, and let me see. So last time, in order to avoid running out of time, let me see. So lecture 4. Now, okay. Okay. So you actually, okay. Well, that was way too fast. You can see the slides, right? Changing this time.
Yes.
Okay, awesome. So see, and I'm just sharing PowerPoint. So it's something with the computer that I was using the other day. That's like super annoying. So we actually did everything up to the reflection and transmission of plane waves. And that's something that I wanted to spend a little bit of time with you. So we just didn't, run through it because it's actually super important. Ultrasound imaging is based on signals reflecting from targets and coming back to the transducer. Most of the modalities, right? Either echographic imaging or Doppler imaging, for example, would revolve around that. Now, in order to understand how this works, there is this very simple scenario, which is the reflection and transmission of plane waves. Imagining that you have this ideal scenario that doesn't exist, where you have two semi-infinite media. It's like medium number 1, from a boundary all the way to the left, and medium number 2 from a boundary all the way to the right. Different properties, different sound speeds, different mass density values, different attenuation properties. You could add that, even though we're going to deal with the lossless case right now, like no attenuation, just to simplify the discussion. You can have all of that, right? And that again would be just a simplified scenario. We are going to study furthermore an even simpler scenario where the plane wave is traveling perpendicular to the orientation of the boundary in between the two media. Because you could also have it, traveling in an oblique incidence. And, it's not all that much different, but, it just complicates things a little bit more. For what we want to learn, this would probably be more than enough. Okay, now, we have a plane wave that's originally traveling, right? It hits the boundary. And when it hits the boundary, there's going to be a wave that's going to go from the boundary into the second medium. That's called a transmitted wave, right? Because, right? And then you have one that comes from the boundary back to the first medium, and that's going to be the reflected wave. We can actually predict how much of the incident signal is going to be reflected and how much is going to be transmitted. And that's the objective of this exercise that we're going to very quickly go through together. Okay, now, in order to be able to solve this problem, right, we have an incident pressure, right? Incident pressure That's going to be something like, I don't know, like E minus J K1, because it's medium 1, traveling in X. We have a reflected pressure field, which is going to be equal to some coefficient, right? Some amplitude, some part of the signal is coming back. How much? I don't know yet, right? That's what we want to figure out. But there's a fraction of it coming back. And then we also have, you know, the plane wave component. So what should be the argument in here of the exponential function? Like I have a medium 1, right? That has some C1, it has some rho 1, right? Like as a consequence of this, there is an acoustic impedance 1. There is a K1 also, which is omega divided by C1, right? And there's a medium 2 in here, so this guy will have C2, and it will have rho 2, and because of that, there is a Z2, and there is a K2, which is equal to omega divided by C2, right? So what should be the argument of the exponential function for the reflected wave?
It should have the change the sign, instead of but everything else will be the same.
Meaning?
Meaning it just changes the direction.
So
possible.
what should I write in here?
Oh, J K1X.
Okay, why? Why not with a
because
minus?
Oh, because it now propagates to the opposite direction.
Correct, because it's traveling to the left. Why the K that goes in there is K1? Because it's still in medium 1, right? Because it's in medium 1, then the wave number should be K1. That's just how it goes. Like on the other side of the boundary, we have the transmitted pressure field, and that's going to be equal to some T coefficient, right? I mean, again, some unknown fraction, right? Then e to the something something. What should be that something something? What should be the argument of the exponential function? Come on, guys, don't be shy. It's actually more fun if you participate.
It is similar to the previous ones, but in this case is also with the minus and using K2 as it is changing the medium.
So it's minus JK2X, right? Correct. So we have basically two unknowns, right? Which are R and T, equal to God knows, right? And how do I actually solve for those two? How many equations do I need? How many equations do I need?
2 equations?
How many?
2?
Yep. So we need 2 equations, right? Now the question is, what should those equations be, right? And the equations that we're going to use come from boundary conditions, really. And basically the idea is that there are some variables that if we go to the boundary in between the two media, right, this thing over here, there are some physical variables that should remain the same shy to the left and shy to the right of the boundary, right? Because in physics, some properties don't change abruptly, right? There has to be continuity in some properties. So the question would be, like from me to you, which properties should be continuous across that boundary?
Sorry, teacher, about the medium or the wave that is propagated?
Well, about the media themselves, nothing, right? Because I mean, they're two different things. So like you said, has to be related to the wave.
The frequency, maybe?
Yes, I agree. The frequency remains the same. The wave number changes, right? But the frequency remains the same. But that would just, I mean, that doesn't help me relating the waves themselves, right? Because the only thing is like the frequency is a known value, which is f, and it's the same on the left and it's the same on the right. But you're absolutely right. The frequency stays the same. What other properties of the waves have to be continuous across the boundary?
Could be conservation of energy.
Meaning?
That if all the incident pressure waves should be transmitted, either reflected.
Yes, actually. And that is something that actually will follow from the equations that would be put together, you know, the way that we're putting them together. I agree, you know, the energy has to be conserved. But thinking in simpler terms, right? We have been talking about fundamental variables. And one of the ones that, or a few of the ones that we have been talking about are the pressure and the particle velocity, displacements, whatnot, and so forth, right? So from this basic description that we have over here, the boundary conditions, right, that we are going to enforce are two: the continuity of the acoustic pressure, because the pressure must be continuous on both sides of the interface. Why is that the case? Why would the pressure have to be continuous across the boundaries? Oh, sorry, across both sides of the boundary.
Action reaction principle, maybe?
Well, let's say that it's not continuous, right? Pressure is force divided by area. If the pressure is not continuous, that means I have more force on one side as opposed to the other one, right? Because, you know, they would be sharing a common differential surface element. So that actually would mean that I have a net force. And if I have a net force, what happens to the boundary? What happens to the boundary if there's a net force?
It will move or deform.
It would move.
Yeah.
Correct. And that's just not happening. I mean, the boundary is in there, it's not moving. So there has to be a balance in there. And the balance comes from saying basically, comes from basically saying this, right? Which is the pressure just on the left of the boundary, which is the incident plus the reflected pressure, has to be equal to the pressure right after the boundary, which is the transmitted pressure. For the sake of simplicity, we say that the boundary is located at x equal to 0. Like we have to say something, right? So this would happen at, you know, x equal to 0. Just because it just makes it simpler. It could be anything actually, and it wouldn't change a thing. Okay, so we just make it x equal to 0. And if we make it equal to x equal to 0, then we just plug the expressions over there, right? And we would have that the incident pressure at x equals to 0 without any loss of generality is equal to 1. The reflected one is equal to r, and the transmitted one is equal to t, right? because all the exponentials evaluate to 1 when x is equal to 0. And that gives us the expression 1 plus r equals to t. So we have one equation, and we have 1. The second equation comes from the continuity of the normal component of the particle velocity, which means that the velocity of the particles in the x direction must be continuous on both sides of the interface. And in this case, that's no problem whatsoever, because, well, assume that this was more vertical, right? But we had the pressure fields, right? And because these are longitudinal waves, that also means that the particle velocities are going to, be happening in the x direction. We're assuming a one-dimensional problem. So the only component of the particle velocity is a normal component. But we could easily have a wave, right, that is oblique to the boundary. And it's doing something like this, right? Which means that there would be a reflected wave that goes like this, and a transmitted wave, like something like this. I don't know, some angle, right? And in that case, the only component that would be continuous is still the normal component. Why don't we need the tangential component to be continuous? Why do we only care about the normal? Why is the normal component the only one that has to be continuous?
Because that is parallel to the boundary, doesn't have any effect.
Why it doesn't have any effect?
Because it's parallel with the boundary.
Elaborate on that idea, please. You're absolutely right, but elaborate on the idea a little bit more, please.
Okay. I'm not sure the part. Maybe
Well,
it have some relation with forces, because
think about it like in terms of, imagine this were to be a highway, right? Like if we have a highway and we have two parallel lanes, does it really matter, if the cars in lane 1 are traveling at, 100 kilometers per hour, and the ones on lane 2 are traveling at 80 kilometers per hour, or 20 or 10? It really doesn't, right? I mean, it's just like one lane has cars going super fast and the other one has cars going super slow. And it really doesn't matter. Imagine, however, that I will have a car from lane 1 going into lane 2, right? Lane 2 is the one with the cars going at 10 kilometers per hour. So I have a car that goes at 100, ramming into cars that are going at 10, and, there's a car accident in there. So it matters, if we have super fast particles are moving super fast, getting in the same location where I have particles moving super slow, or vice versa, right? I mean, same thing. I have, one of the super slow cars getting into a super fast lane, and then all the cars are just like ramming into it, and again, horrible car accident, right?
because all are in the same direction.
Correct, because they happen in the same medium. The tangential one, it all happens like the particles moving in the tangential direction, or the component it happens like everything that's in medium 1 stays in medium 1, and everything that happens in medium 2 stays in medium 2. So it really doesn't matter if in that y direction, right, things are like moving differently, because those particles don't interact. They exist in 2 different media. But the normal component is different. Because what you would think is that, if I have, again, particles reaching the boundary very, very fast, and then coming very, very slow, I would be accumulating particles in the boundary, or the other way around. You know, they're arriving at a certain speed and they're leaving much faster than that. Then I'm going to create a vacuum in the boundary. And near one of those look really good, you know, like physics-wise, although it would be super cool to be creating some sort of a, but anyway, so that doesn't happen, unfortunately, right? I mean, sad face. I see that Piero is raising his hand. So do you want to add something to the discussion?
Yeah, maybe. Well, it could be another reason that it couldn't be like this kind of shear waves, right? It could be a shear wave. If
No, it wouldn't be.
propagating.
Actually, it's not a shear wave. It's still a longitudinal wave. Like whenever you have a, like remember, I can be like in a two-dimensional space, right? That doesn't exist, but what the heck, right? And maybe like a wave is propagating in this oblique direction. I don't know why every once in a while this does this crazy thing. Anyway, which means that your particle velocity, right? Let's say that the particles are moving in this direction. It just means that, you know, it's traveling, you know, there's a component in X and there is a component in Y. And in this case, it's roughly, it looks like a 45-degree thing. So it just means that the velocity has a component in X and a component in Y. But the wave is propagating at, let's say, 45 degrees, right? So it is an oblique wave. And remember that the difference, like what separates shear waves from longitudinal waves is that in the case of longitudinal waves, the energy propagates in the same direction as the direction of propagation of the particles, right? So particles are moving in 45 degrees and the energy is also moving in 45 degrees. Shear waves would be the opposite. The energy is moving in, you know, 45 degrees, but the particles are moving perpendicular to 45 degrees. And that would make it a shear wave. Now, if you have an oblique wave traveling, like a wave that's originally a longitudinal wave, and it reaches a boundary, and you have solid media, just to simplify the discussion, let's say that on both sides you have solid media, right? Although it can be, it doesn't necessarily have to be as stringent as that. You can have a fluid medium in one of the two ends. But you can actually generate shear waves. There can be mode conversion. Yes, that can happen. Mode conversion in the sense that part of the longitudinal waves would become shear waves in the transmitted side, for example. And part would still, you know, remain their longitudinal behavior. But for that, you would have to be propagating in solid medium. That's a consequence of propagation in solid medium. And then you will have mode conversion again. But that's not what we're talking about in here. We're assuming that that boundary separates to fluid media still, right? In everything that we're going to be discussing in these upcoming lectures, we're still assuming it's longitudinal waves, it's solid media. It's fluid media. So no, even though you have, you know, oblique incidence, even though you have longitudinal components in X and Y, it's still a longitudinal wave. It's just that it's traveling oblique. Okay.
Yes, right. Thank you.
Okay. So we don't have to have the velocity again be continuous in Y. We need it to be continuous in X. And we arrive to an equation that's similar to the one that we have for the pressure, which is that, you know, and this should probably have, you know, some X in here and X in here and X in here, but regardless, the particle velocity normal component of the incident wave plus the one of the reflected wave has to be equal to the one of the transmitted wave, which brings us to, well, actually to this. Why? What is the particle velocity of the incident field? What would it be equal to? That's equal to the incident pressure divided by the acoustic impedance of medium 1, right? Maybe you remember from our discussion on last Thursday, the acoustic impedance is a ratio of the pressure divided by the particle velocity, right? So we can actually say that particle velocity is the pressure divided by the impedance. What about the reflected particle velocity? What would it be equal to? Do you guys remember?
PR over C2. Over
It would
C1,
be
sorry.
PR divided by
C1.
Z1. Anything else?
Oh, multiplied by the
There's a
PR.
minus in there. Why is there a minus in there?
Oh, because of the direction.
Correct. Remember that, you know, for plane waves, the absolute value of the acoustic, the specific acoustic impedance is equal to rho times C, or the characteristic impedance. But the sign differs. For a wave traveling to the right, it would be with a plus. Traveling to the left, it would be with a minus. Depends on the sign convention that you use, okay? But you know, get used to it. And then for the transmitted field, it would be equal to what? The transmitted particle velocity in the x direction, which in this case, it's the only direction anyway, right? It would be equal to what? It's equal to?
Transmitted pressure divided by the impedance of the second medium.
The second medium, correct. And that's how you have that expression over there, because remember, our boundary is still located at x equal to 0, which means that the incident pressure field, the way that we have defined it, again, without any loss in generality, is equal to 1. The reflected pressure is equal to R, and the transmitted pressure is equal to T. So that's where you have that second equation in there, 1 divided by Z1 minus R divided by Z1 is equal to T divided by Z2. You have two equations, you have two unknowns, and you know, this is one of the simplest equations probably that you're going to have to solve, you know, in a context of a course like this. And these are the expressions for the reflection coefficient and the transmission coefficient, which are the names for R and T. Okay, the reflection coefficient is equal to the impedance of the second medium minus the impedance of the first medium divided by the sum of the two impedances. For the transmission coefficient, you have 2 times the impedance of the second medium divided by the impedance of the second medium plus impedance of the first medium. Okay, you're gonna get used to it eventually, you know, and so anyway, and if someday you want to branch out into telecommunication systems and you study transmission lines and coaxial cables and stuff like that, then you're going to see those equations and you're going to be like, well, what do you know? You know, I learned something that, you know, can also be used in a completely different field of study. So there's a few things that, you know, are important for you to be mindful of. This is a table that comes from Thomas Sabo's book on acoustic waves. You know, it's an ultrasonic imaging actually, but it deals a lot with the physics of ultrasonic or acoustic waves. And these are some values that are provided just for reference. You know, I'm pretty sure you can find some other, you know, compiled values in different textbooks and articles and such. But it's just to give you an idea, you know, of some acoustic properties of tissues, you know, how do they change? And for example, you have blood, right, which is mainly water, and it has a speed of sound of 1584 meters per second. It's relatively unfortunate that, you know, the number that you have for reference is water at 20 degrees. You know, I should probably ask Tom to update this, because it would be far more relevant that you would have the value of water at 37 degrees. The temperature actually has an effect also on the value of the sound speed, by the way. You would probably know that. And And there are complete articles that are devoted to tell you, you know, how the sound speed in water changes as you change the temperature. It's kind of neat, and you have equations and you can sort of calculate it. But from here, right, I mean, you can see that most of the soft tissues, you know, are, because of their water type component, have values of sound speed, which are all in the ballpark of, you know, 15 something, you know, like 15 whatever meters per second. And actually, for soft tissues, we typically assume that the sound speed is approximately 1540 meters per second, which, you know, if you look at this compilation, it seems to be on the lower side, you know, of the spread, certainly in the much lower side, but, you know, it's just a referential number. So, for example, whenever you have scanners configured, they would probably be shooting for something like 1540 meters per second, just like a default value that every scanner would have encoded when, you know, performing ultrasonic imaging. The different number in here would be fat. And that in itself, you know, like determining what the value is for sound speed of fat is also kind of tricky and complicated. But the sound speed is actually much lower in comparison, which, you know, it's what it is. I guess for me it's intuitive, you know, and second nature because of so many years of looking at it. But in case you didn't know, you know, sound propagates slower in fat than it does in water. So, you know, that's just what it is. The other value that's incredibly different in here would be the one of bone, which, by the way, is not a soft tissue. So it would actually, you know, generate mode conversion, and you will have shear waves too, and, you know, all that complicated stuff, because it's not like a fluid type medium. Actually, even soft tissues are not exactly fluid type. If they were to be perfect fluids, then the whole field of elastography wouldn't exist, okay? But the sound speed in bone is much higher, as you can see. But if you take bone out of the equation, and even if you keep the fat, right, which is not all that different, you can see that all those values of sound speed are very similar. And moreover, you can see that all the values of density, you know, like this and 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 this, you know, like probably excluding this one, of course, which is the one of fat, which is somewhat different. And we know that fat has a lower density compared to water, because we know that fat floats on top of water, right? We see that everything else has a density of about, you know, 1,000 kilograms per meter cube, sorry, which is expected, because, I mean, if it's like very soft tissues, they're mainly water, you know, which you already know, like most of your body is water, then the sound speed and the density of every soft tissue is not that much different than the one of water, which is 15, like it's in a ballpark of 1,500 meters per second for water and 1,000 kilograms per meter cube. And this has very profound consequences for ultrasonic imaging. Yes, I think there's a question in the chat. Let me check. Oh, so Pierrot is asking what is mode conversion. Mode conversion is what we were discussing earlier. You have a longitudinal wave and it reaches an interface. And when it reaches an interface, it should generate a second longitudinal wave, you know, as a result of transmission. But when you have oblique incidence and a longitudinal wave travels from, you know, some medium into a solid medium, part of the wave is going to still propagate as a longitudinal wave, and a part of it is going to propagate as a shear wave. So a longitudinal wave can produce a shear wave. And that mechanism is called mode conversion, because it's a different mode of propagation, right? It goes from being longitudinal to being shear. Okay, so that's what it is. And again, you know, it's Mode conversion doesn't mean that the whole wave becomes, you know, a shear wave. It's just part of it becomes a shear wave, but the mechanism is a mode conversion. Sure, no problem. Okay, so this will have like this similarity of the sound speeds and the densities means that there is also a similarity in the values of the impedance, which are, you know, all of them approximately in the ballpark of 1.5 mega rails, where, you know, you can actually figure out the units yourselves, right? Which is in units of kilogram per surface of area per second is the value, or that's the unit of the intensity, the impedance. So if the sound speed is about, you know, 1500 meters per second and the density is about 1000 kilograms per meter cube, then the product is about 1.5 times 10 to the 6th power. So that's where the mega rail comes from. It's a 1.5 mega rail value for the impedance. So that's roughly the value that you should be expecting to see, and it really doesn't change a lot from tissue to tissue. Okay, so that's one thing that's very important, because it means that soft tissues generate, like, interfaces from one to another soft tissue generates waves of very, very low amplitude. And that is actually something that allows ultrasonic imaging to exist. Because if the reflections were to be super strong, then you would be screwed. I mean, it's like you would have the incident wave, it finds an interface, and most of the wave goes back, you know, for example, and none of it goes through. And then you just don't have enough energy for the wave to keep propagating. The fact that the wave is losing tiny amounts of energy as it keeps propagating actually makes ultrasonic imaging viable. But it's also very important for you to know that because of the nature of the impedances being relatively very close, the echoes that are being produced range from some tiny minute echoes to relatively large echoes. And they can actually span orders of magnitude, which is the reason why we're going to see that afterwards. For ultrasonic imaging, we display the amplitudes of the echoes, not in linear, but in logarithmic scale. All of this, again, comes from, you know, these fundamental concepts of how the waves are propagating. And it just all comes from that. You know, you have impedances, again, that are relatively close, but in one case, you know, maybe your first impedance, right? Maybe your first impedance is going to be equal to like 1540 meters per second, and then the second impedance is going to be equal to, let's say, like 1530 meters per second, right? And let's assume that the density is 1000 for everything. So the difference in here would be, you know, 10 units of sound speed, and that would be 10 to the 4th, right? I mean, in impedances and such. And you can easily see that if we have a Z1 of 1540 and we have a Z2 of 1539, for example, which can happen, then the differences in impedances would be an order of magnitude less, which would actually make, you know, the reflected pressure field to be an order of magnitude less. So the intensity would be 2 orders of magnitude less. And there you get to see the spread of, you know, dynamic ranges that would be existing in your image. If you were to display this in linear scale, you wouldn't be able to see an echo from this second scenario, because the first one would be 10 times larger and you wouldn't see any difference. So keep that in mind. I mean, it just comes from that, you know, that relatively limited contrast, if you display on linear scale, comes from the fact that all the echoes are coming back from tissues that are very similar to each other. So you're looking at minute differences that depend on how minute they are, you know, they can very widely change the dynamic range in your image. The second one is that, you know, remember there were 2 things that were different in that table. Actually, we only talked about one, which was bones. bones have a larger sound speed and a larger density. So they're going to reflect much of the acoustic energy that hits on them. And that's one of the reasons why ultrasonic imaging is not really very much used for imaging of bones. And actually, you cannot see much of anything when you're going through a bone, you know, of the soft tissues after it. So that's one thing that will have a practical consequence. The other one that has, you know, a practical consequence that we didn't talk about is this little guy over here, air. Air has a sound speed of 343 meters per second at 20 degrees Celsius of temperature, which, you know, it's lower than 1500, but it's not that bad. I mean, it's kind of bad. But the one that makes it super bad is the density. Super bad. That's like a movie reference from the early 2000s or something. But anyway, when you look at the density, right, everything is in the ballpark of 1,000, and all of a sudden you have air, and air has a density of 1.21, but you kind of get the point. So your acoustic impedance, you know, it's lower than, you know, 3 orders of magnitude when you compare air to any other type of tissue that you find in your body. That's super small. Like that impedance looks like 0, you know? And when you have such a large difference in impedance, you are not going to get a good transmission. You simply won't. You won't get anything transmitted into the second medium. So you don't get acoustic signals propagating into air. And that has 2 consequences. The first one is that, for example, ultrasonic imaging pretty much sucks when you're trying to do imaging of the lungs, unless you're doing imaging of the surface of the lungs. That you can do, but inside of the lungs, that you can never do with ultrasound. The second one, which is probably, you know, even more common, is the fact that even the air, you know, surrounding the transducer, if I just grab a transducer and place it on top of tissues, and I expect the ultrasound waves to propagate into the tissues, that's just not going to happen. And it doesn't happen because there's air in between the transducer and the tissues. Even if it's a tiny amount of air, you know, like a thin layer, just because you place the transducer on top, that thin layer of air is going to prevent any ultrasound making it into the tissues. So what you will have to do is, you know, you will have to be pushing the transducer down to the point where it's actually painful. And that just wouldn't fly. What we do in practice, which you probably have, even like if you have seen an ultrasound scanner, then you know that's what it is. And if you haven't seen it, you've probably watched movies or something, and you know that you actually place a coupling gel in between the transducer and the tissues, right? So you have the transducer, you put gel on top of it, like tons of gel, and then you start navigating, right? You move it a little bit, and then you start scanning, because the gel is basically water, and it's acting as a couplant in between the transducer and the tissues. And because it's mainly water, and your body is mainly water too, the soft tissues in your body, then there's a very good coupling, you know, in between the waves leaving the transducer, going through the gel into your body. And you get a very strong reflection, you know, from the inside of your body, and you can construct the images. Otherwise, you couldn't. Okay, so if you ever wondered why is it that people use gel, you know, to couple the transducer to your body, that's the reason why. And all of these things, again, come from very first order, you know, observations that we can derive from this very, very simplistic model of the transmission and reflection of ultrasonic waves in between 2 semi-infinite media. Questions? No questions? Yes, Brett, go for it.
Well, yeah. Well, I got a little bit confused with how the impact in the dynamic range of the image means the
Sure.
difference in impedance. So I didn't understand. I mean, I know that the difference in impedance prevents the wave from propagating from one side to the other, but why does it affect like the complete dynamic range of the image at the point that you cannot distinguish any other structure?
If you were to display it in linear scale, you wouldn't.
Oh, okay.
Because
But in the
again,
logarithmic, yes.
correct. Because
Okay.
in principle, your impedance is going to be approximately, right? I mean, again, don't cite me on this, but let's say, 1.5, plus some delta megareals, right? Like something like that. And the issue is, what the value of this delta is. Like if most of these deltas were to be large, then nobody would probably even care. Or they would spread a relatively large, range of, or sorry, not a strangely large range of values, then nobody would care. But the problem is that that delta can actually span several orders of magnitude. And those are relatively small quantities. And that basically, will produce your echoes to span several orders of magnitude. And in order to display them properly, you will have to logarithmically compress, or something else. But that's the solution that people in the radar and the ultrasound community and the sonar community found like many, many, many years ago, and we're just still using that.
Okay.
Mm-hmm.
Thank you.
Sure. Okay. No, it's correct. Okay. And now it's 7:03. So, I mean, I saved it, to talk with you about transducers, but I didn't think we were going to make it. So I just had the materials in there. Given that it's already 7 p.m., I think we should probably like stop in here, which is where I actually planned on making it. The one thing that I wanted to also let you know is that next Thursday, like on our next lecture, we're going to have our first quiz. So that's going to be super exciting. Remember that, the way that the course works, you will have homeworks, but you will also have quizzes. And our first quiz is going to be, well, I'm actually going to work it related to ultrasonic imaging. So we're not going to have a quiz on, the fundamentals of like the math behind medical imaging, just because, so our first quiz is going to cover concepts that we studied either on the first day lecture or on this lecture. And it will happen towards the end of the lecture on first day. So it's roughly going to take the last 20 minutes of the lecture or something like that. Okay, just so you know. Questions, comments? Okay, so given that I think there are no more questions or comments, we can adjourn the class. Thank you guys for being here. Breno, just to wrap up the conversation about the like the things that you said that were missing on the Pangea side and stuff, maybe you can stay and we can square it out right now. So everything is okay in the Pangea side. Okay, that works for me too. Thank you guys. Have a great rest of your night.
Thank you.
Bye guys.
Also, look at the chat. I'm sending a lectures for all the week, so they can maybe put suggest the best hours for them to have the office hours.
Sure. Okay. Thank you guys.
Thanks, teacher.
Bye.
Bye, teacher.
Bye.
Thank you.
Bye.
Guys. Let me see. So you're saying the Zoom IMG, let me see. 340. Okay, so lecture 1. Okay, so yeah, I'm looking at the
Oh, the last one.
idea.
Yeah.
Right, so let's see. So it's lecture 1 recording. Can start. Okay, so let me see. We can switch to Spanish too. And let me actually stop the recording.